Okay, so this question is asking us which compound is used as a standard for NMR chemical shift measurements. So the first thing we need to clarify here is what exactly an NMR standard is. And a standard is a substance that's included in sort of every NMR sample that's going to be put through an NMR spectrometer to give a well-defined peak that everything else is measured relative to. So NMR doesn't have like any absolute peak values, they're all measured relative to a standard that's included with the sample. So the first thing that we need to check is that all of these all of these compounds actually produce a peak in both carbon and proton NMR. They're the most common ones. Other types of NMR might use a different standard to the one we're going to talk about here in this question. But the first thing we should be checking with these is whether they actually produce a signal in both carbon and proton NMR. So the first one that's drawn my attention is D2O. This doesn't have a carbon in it, so it won't produce a peak in carbon-13 NMR. In the same vein, this is deuterated water, so D2O rather than H2O. Also, no peak in proton NMR, because D is the same as heavy hydrogen. It's just got an extra neutron, which is sometimes called heavy water, deuterated water. D, in the same sort of idea, we've got tetrachloromethane here. This is not going to produce a peak in hydrogen NMR. There's no hydrogens in this compound. We're not going to get a peak in hydrogen NMR. Same problem with this. This is deuterated trichloromethane, otherwise known as deuterated chloroform. And this does have a carbon. It has deuterium rather than hydrogen though, so this is going to have no peak in hydrogen NMR. And in reality, all three of these, B, C, and D, are actually good NMR solvents. It's very desirable for a solvent not to have a strong peak in your NMR spectrum. So it's actually good that these don't produce peaks most of the time because we use them as solvents. So the one that's left over is tetramethylsilane, and this is a really good NMR standard because we have lots of peaks, lots of carbon atoms, hydrogen atoms in the same environments. So we've got 12 hydrogens that are all in the same environment. We've got no adjacent hydrogens that are going to cause any splitting, so this is going to create a singlet peak that's very intense from a small amount of tetramethylsilane, because we've got those 12 hydrogens in the same environment all contributing to the same peak. And the same is true with carbon. We're just going to get one peak that's going to be quite intense because we've got 4 atoms all in the same environment. So here the answer is going to be A. Okay, in this question we need to identify which compound is a secondary amide. So first of all we need to double check that we're sure what an amide is and what a secondary amide is as well. So an amide is a functional group where we have this carbonyl acetable bondo directly bonded, single bonded to a nitrogen, and then this carbon and nitrogen can be bonded to other things as well. So I'm just going to put R1 for there, and this will usually be, some carbon chain or something, and then our amides classification is going to be decided in the same way that an alcohol is classified, or an amine as well. It's going to be decided based on how many carbons this nitrogen is bonded to. So the lowest classification for an amide, because we have to have this single bond between the carbonyl and the nitrogen, is primary. And then we also have secondary amides, if this nitrogen is bonded to another carbon and a hydrogen, say. And then we can also have a tertiary amide when the nitrogen is bonded to 3 carbons. So in this case, we're looking for a secondary amide. So we want our nitrogen to be bonded to 2 carbons and 1 nitrogen. So maybe something along the lines of this structure. It doesn't actually matter what comes off here or here. We're looking for this secondary amide. So 2 carbons bonded to nitrogen. So let's have a look at these 4 structures and see which ones contain an amide functional group to begin with. So A doesn't. We've got a carboxylic acid and an amine here, but no amide because this nitrogen isn't bonded to the carbon. So it's not A. Same problem with B. We've got the carboxylic acid and the amine. So these are not amides. So now we've got C and D, which both have this amide functional group. We've got the nitrogen directly bonded to the carbonyl group. We need to look at how many carbons each of these nitrogens are bonded to. So here we've got 1, 2, 3, and here we've got 1, 2. So this is going to be secondary amide, and this is going to be a tertiary amide. So our answer is going to be C. This question asks us which compound does not react with nucleophiles. So the first thing we need to establish here is exactly what a nucleophile is, so that we can figure out what it will and won't react with. So a nucleophile is an electron pair donor. Examples of nucleophiles that you might have seen in class might be something like a hydroxide anion or ammonia, where they can both donate these lone pairs that they have to centers of electron deficiency. So the things we're looking for in the compounds for something that will react with a nucleophile is a center of electron deficiency, and the compound that won't react with a nucleophile is something that doesn't have a center of electron deficiency. So if we draw out these compounds, it's going to help us to figure out which ones do and don't have centers of electron deficiency. So first of all, we've got A, this is propanal. B is propene. C is butanone. And D is 1-chloropropane. So there are 3 of these compounds that have centers of electron deficiency. So starting with A, we've got propanal, where we've got this carbonyl, and this oxygen is more electronegative than the carbon. It's better at pulling those shared pairs of electrons towards it, which makes this carbon delta positive and the oxygen delta negative. So a nucleophile is very happily going to attack this carbon here because it's short on electrons, and the nucleophile has electrons to give. Compound C, butanone, we also have this delta positive carbon for the same reasons as in propanal. And in D, we also have a delta positive carbon because this Cl is, the chlorine is more electronegative than the carbon, so it pulls those electrons away from it, meaning this carbon is slightly electron deficient. In propene, we don't have a center of electron deficiency. In fact, this alkene carbon-carbon double bond is a center of electron, sort of high electron concentration, and that is not going to react with a nucleophile. So here, our answer is going to be B. So this question asks us which structure represents an alicyclic compound. So the first thing we need to talk about here is exactly what an alicyclic compound is. And it's sort of a compound noun, it's 2 different words stuck together. both of which you might have heard before. So ali refers to aliphatic, and cyclic is just cyclic. So we're looking for an aliphatic cyclic compound. And aliphatic is non-aromatic, so it's sort of a less used word now, but it just means anything that isn't aromatic. So for instance, an alkyl chain would be an aliphatic chain. So in this question, we're looking for a compound that has a cyclic system that isn't aromatic. So it doesn't have a benzene ring, for instance. So B, for example, has a benzene ring, so that's aromatic. So our answer isn't going to be B. A has got this really large aromatic system. It's two benzene rings that are stuck together. So this is also not our solution. It isn't aliphatic, even though it's cyclic. Then we're left with options C and D. D quite clearly includes a benzene ring. This is more how we tend to draw this at A level. This is also a benzene ring. It's just drawn with the 3 double bonds instead of the circle inside. So D also isn't going to be our answer. We do have an aliphatic section, unlike A and B. The whole of these molecules are aromatic. In D, this is aliphatic, but it isn't cyclic, so D isn't the answer. And in C, we have a cyclic structure, which is also aliphatic because these double bonds aren't sort of delocalized across this whole ring, they're localized into this space. So our answer here is C. In this question, we need to figure out which molecule is not planar. So the first thing that we should do here is to draw the structures of the 4 compounds so that we can figure out which one isn't going to be the planar one. So first up we have ethene. So we have these 2 carbon-carbon, we have the carbon-carbon double bond and then the 4 hydrogens around it. Next we have ethane. Then we have methanal, and finally hydrogen cyanide. So we need to figure out which molecule isn't going to be planar, and the kind of hint here is we're looking for the odd one out, and 3 of these have multiple bonds, as in a carbon-carbon double bond, carbon-oxygen double bond, or in hydrogen cyanide, the carbon-nitrogen triple bond. These tend to make molecules planar, so for instance in ethene, the bond angle around all of these is 120 degrees and the molecule is completely flat. The same is true in methanal, and hydrogen cyanide is linear, so this is 180 degrees here. So the answer here is going to be the ethane. It's because we have these tetrahedral shapes around each of the carbons, which is going to make them non-planar. This question asks us, what is the number of peaks in the hydrogen NMR spectrum of this compound? So first things first, we should definitely try and draw this to see which hydrogens are going to be in which environments and if we have any sort of lines of symmetry or anything like that. So we need to first look for any kind of symmetry in our molecule, and we can see that if we draw a line down here, the compound is the same to the right and to the left. So how many environments are we going to have? Well, our first environment will be these 4 hydrogens. These are going to be the same, so I'll number those all as 1. this will be in its own environment. 2. This on the alcohol will be 3. And then we've got 4. So we're going to have 4 different environments, which is going to give us 4 different peaks in our NMR spectrum. So the answer here is B. In this question, we're told that ethanol can be prepared by different reactions. And we've been asked which reaction has the lowest atom economy. So atom economy is a measure of the percentage by mass of all of the reactants that end up in the product, the desired product. So in this case, ethanol is our desired product. So we need to look at each of these reactions and we need to figure out which one has the lowest percentage of atomic mass in the desired product. So first of all, B catches my eye because we only have one product, and the only product here is ethanol. So if we only have one product, then every single atom that was in our starting materials is in our desired product. So it can't be B because that gives us an atom economy of 100%. Sort of along the same vein, with A, CO2 is quite a low formula mass compound. It's 44. We've got one of those per ethanol. This also likely isn't going to be our lowest atom economy process. So we're left with C and D, and we have an option between hydrogen bromide and ethanoic acid. And a really good thing to look out for with atom economy questions is having a side product, a product that isn't your desired product, that has a halogen in it or a halide, because they tend to be quite high atomic mass. So bromine 79.9, iodine is even heavier, and often if you have one of those atoms ending up not in your desired product, it can really lower the atom economy of the process. So the answer to this one is C. And obviously we haven't really worked through the atom economy of each answer here, but this is a 1-mark multiple choice question. We shouldn't be using our equations. We shouldn't be adding up the formula mass of every single compound in this question to double check which one it is. If you were unsure sort of between C and D, you could absolutely break out the formula for atom economy, which is the formula mass of the desired product over the total formula mass of all of the reactants times by 100. But here the answer is C because that hydrogen bromide is a really heavy side product. This question tells us that the breakdown of ozone is catalyzed by nitrogen monoxide radicals, NO radicals. So that's a really key piece of information here to begin with. We know we're talking about the breakdown of ozone by NO radicals. So which equation is a propagation step? So propagation is one of the 3 parts of a radical mechanism: initiation, propagation, and termination. And I guess one really important thing to talk about here is that this says catalyzed, which means that our NO must be reformed during the process or left over, which is going to help us with this question quite a lot. So if we think about the first propagation step that we can definitely say exists, is that a nitrogen monoxide is going to react with an ozone to give us NO2 and oxygen, O2. And we know, we might know that the overall equation for ozone breakdown is O3, it's a reversible, 2O3 forms 3O2. So we know that oxygen is a product molecule here. That's not going to carry on in our propagation process, but this NO2, we said before that we need to reform this NO so that it can break down more ozone because this is a catalyst. So that NO2 is going to be the one reacting, and that's going to be our second propagation step. And there's only actually one option that has NO2 in its equation. So the answer here is going to be D. This NO2 reacts with an oxygen atom to reform this NO radical that's going to break down ozone and our second molecule of oxygen in this process. So our answer here is D. In this question, we're asked which compound could have produced the IR spectrum below. So we've been given these 4 organic compounds, and let's start off by drawing them just to make sure that we can identify what functional groups they have. So this first one is ethanol. The second one is a nitrile that has an alcohol in it as well. So we've got 1, 2, 3 carbons. There's a triple bond to the nitrogen on the end. And on this second carbon, we also have an alcohol. For compound C, we've got ethanoic acid. And for compound D, we have an amide, ethanamide. Okay, so IR is this analytical technique that transmits radiation of a certain wave of range numbers between like 500 and 4,000 wave numbers, and we measure how much of it is absorbed as a measure of how how often a bond appears in that sample. So each bond has a specific wave number that it absorbs at. So for instance, this really sharp peak here around 2,300 is going to be because of a particular bond. And if we just have a look now, I've got the data table for IR from this question, and we can see that something around 2,220 to 2,260, I eyeballed this and said it was about 2,300, is a nitrile. So that's a super good place to start. Only one of our compounds has a nitrile in it, and that's B. But if this IR spectrum was produced by B, then we should also see this OH bond appearing for an alcohol, which is like a large, broad peak between 3,200 and 3,600 wave numbers, which we can see here also. So this is an alcohol OH group. So with those 2 peaks in mind, I think we can safely say that this is B. To rule out some of the other possibilities, for instance, C and D both have carbonyls in from different functional groups, but nevertheless, these usually appear around 1700, and we've got sort of a glaring gap here without any big peaks between 1500 and 2000. That really quickly tells us that it isn't either of these carbonyls. And then in compound A, though we would have this big peak at about 3,500, we definitely wouldn't have this peak here due to the nitrile functional group at about 2,300. So the answer here is certainly B. In this question, we're told that benzene reacts with an organic reagent in the presence of a halogen carrier to form phenylethanone. So here's the sort of overall reaction. We're going from benzene to phenylethanone. So what's changing? Well, we are going to be swapping out this hydrogen for this carbonyl group. And we need to think about how that's going to happen, and this is an electrophilic substitution mechanism. So what does that mean? Well, we know that we're substituting this hydrogen for this group here, this ethanone group, and we can figure out that this has to be by an electrophile because we have an electron dense system here. So this is only going to attack something that is positively charged. And in the case of benzene, it needs quite a strong electrophile, something that actually has a full positive charge rather than just a partial positive, because the benzene ring is so stable. The molecule is much more stable than you'd expect. This is part of the syllabus earlier on in comparison to cyclohexatriene. Benzene's much more stable than that, and that comes from this delocalized ring system. So we need to think about which of these options, which of these reagents is going to be able to form a positively charged cation. So first of all, it's going to be good to draw all of these options to see which one is going to work. So first of all, we have ethanol, then we have ethanal, then we have ethanoyl chloride, and finally ethanoic acid. So we need to ask ourselves, how do these form carbocations? Well, they react with this halogen carrier that was alluded to in the question, which is usually something like AlCl3. And that pulls off an atom, a leaving group, and leaves behind a carbocation. So we know that we want to form this carbocation to give us this group. So when the ring attacks the carbon, we're left with this group on here after the hydrogen falls off. So the first option we can eliminate is ethanol. Oh, I've made a mistake drawing ethanol there. It's one too many carbons. So ethanol isn't going to work. It's an alcohol. It doesn't have this carbonyl group. It's not going to be able to form a stable carbocation. And we're left with these three carbonyls that all have different groups on here. And one of these is going to have to act as a leaving group. So if we think about what the leaving group would be for these three compounds, it would be H minus, Cl minus, or OH minus. H minus is by far the least stable of these options. Hydride anions do form sometimes, but really not very commonly as a leaving group. You should only really be seeing these when they're sourced from something like sodium borohydride as a reducing agent. And then we're left between chloride and hydroxide anions, and we need to think about their relative stability. So whichever negative ion is more stable is going to be the better leaving group and will be more likely to form this carbocation that we want to. So the best way to think about this is quite complicated. The best way to think about it is to think about the acids that would form these conjugate bases. So if we have HCl versus H2O, both of these just adding a proton. If we think about HCl, it's a strong acid that will fully dissociate into H plus and Cl minus, whereas water is weakly acidic and will split into H plus and OH minus in equilibrium rather than fully dissociating. So the answer here is going to be C. Just to clarify, the reason that this is more stable is because we know that the acid more readily dissociates when we have a more stable conjugate base. In this question, we're asked how many straight chain structural isomers of C7H15Cl contain a chiral carbon atom. So first of all, we need to make sure that we're only drawing straight chain as opposed to branched chain structural isomers of this. Furthermore, we need to be sure that we know exactly what a structural isomer is. So a structural isomer is a compound with the same molecular formula, but differing structural formula. Furthermore, we need to be sure that we know what a chiral carbon atom is. And a chiral carbon atom is any carbon which is bonded to 4 different groups. For example, we could have something like carbon bonded to hydrogen, an alcohol group, and then a methyl and an ethyl group. This would be the chiral carbon here, and sometimes we annotate that by putting a star next to it. So we've got this compound C7H15Cl, and the first thing that we can figure out here is if we use the general formula for an alkane, a straight chain alkane, it's CnH2n plus 2. And if we think about the carbons versus the other groups here, this C7 compound would be C7H16, telling us that this is like a saturated straight chain molecule. We're not trying to add in any double bonds or any ring structures, anything like that. So we can start off by drawing a 7-membered chain. 1, 2, 3, 4, 5, 6, 7. So this is has an odd number of carbons in the chain, which means that we're going to have a line of symmetry down the center of the molecule, which means that moving chlorine to the left or to the right, if we started with the chlorine in the middle, moving it to the left or to the right is going to form the same molecule. So we're only going to move to the right in this question to make sure that we aren't doing any repeats. So let's just move this chlorine along the chain each time until we have all of the straight chain structural isomers. So now we need to examine if any of these carbons are going to be chiral. The rest of the carbons in the molecule aren't in each of the cases because there's 2 hydrogens on each of these. So we're only looking at the carbons that have the chlorine directly bonded to it. So we've got also a hydrogen on here. Is this molecule, does it have a chiral carbon? Well, this group and this group are going to be the same. We've got 1, 2, 3, and 1, 2, 3 carbons. So this is not chiral. In molecule 2, option 2, we've got carbon bonded to hydrogen and chlorine. We've got it bonded to an ethyl group and also a 1, 2, 3, 4 butyl group. So this is going to be chiral. Our carbon here is bonded to 4 different groups. And the same is true of this molecule here. We've got a methyl, and this is going to be a pentyl now. So this is also chiral. And finally, we're left with this one, and chlorine's on the terminal carbon now, the final carbon in the chain, which means there's also going to be 2 hydrogens on here, making this not chiral since we have 2 identical groups, the same as our first molecule. So we've got 2 molecules that are chiral here. Our answer is going to be B. In this question, we're shown the mass spectrum of this compound here. And we're asked to identify which ion is responsible for the peak with the greatest relative intensity. So which ion is responsible for the peak with the greatest relative intensity? So let's identify that peak first. That's going to be the peak that has the tallest peak, the one that's largest on the y-axis, has the largest y-axis value, since the y-axis is relative intensity. So this peak is at an m over z of 43. So we need to look at the ions that we've been shown and to check what each of their masses are. So first of all, we've got A, 2 carbons, 4 hydrogens, and an oxygen. That's going to be 44, 24, 28, 44. We've got 3 carbons, 36 plus 6, that's 42. We've got CH3, 2, it's 30, plus 12, 42, plus 1, 43. And CH3CO, that's going to be 27, 43. So we know that the shift of our peak, the m over z, is 43. We can eliminate A and B since they don't have the correct m over z value. We've got a charge of 1, a formula mass of 42 and 44, so their m over z's would be 44 and 42 respectively for A and B. We're left with C and D, which both have this value of 43. The best thing to do here is to draw these ions to see if they could feasibly be formed during the breakdown of our original molecule. So let's draw our original molecule and also draw ions C and D. So to have this positive charge on this carbon while also only being bonded to CH3 and oxygen, this is going to have to be a carbonyl. Our original molecule only has an alcohol in it, and we can only make one sort of break to the molecule. We can't move any bonds around to form these ions per se, which means that ion C is definitely going to be the one that's forming here. This breaks, and we're left with a positive charge on that carbon there. So our answer is option C. In this question, we're asked which statement or statements supports or support the delocalized model for the structure of benzene. So first, we should establish exactly what the delocalized model for the structure of benzene is, and that's this one that we draw with the hexagon with the circle inside of it. And the alternative structure is Kekulé structure, which has alternating double bonds in 1, 3, 5 positions. So we've been given these 3 statements. We need to assess which ones support the model, the delocalized model for the structure of benzene. So number 1 is all carbon-carbon bonds have the same length. And if we think about the delocalized versus the Kekulé structure, this delocalized system above and below the plane of the carbon-carbon bonds is supported by all carbon bonds being the same length. In Kekulé structure, you have alternating bonds between short for the double bonds and long for the single bonds. And in the delocalized model, we'd expect all 6 carbon-carbon bonds to be the same length because that delocalized cloud is contributed to and shared equally by the 6 carbons. Number 2 is that the enthalpy change of hydrogenation of benzene is less exothermic than expected. Well, this enthalpy change of hydrogenation is where we add 3 H2s to the double bonds in the 2 systems to turn them into cyclohexane. And it's saying that this is less exothermic than expected. If we think about exo versus endothermic processes, bond making is exothermic and bond breaking is endothermic. So we have the same molecule as the product for these 2 reactions, which means that the same bonds have been made. But if the overall enthalpy change of hydrogenation for the delocalized structure, that's going to be less exothermic than for Kekulé's structure because of the stability offered by the delocalized system. The bond breaking, which is the endothermic process, is going to require more energy. So statement 2 also supports the delocalized model for the structure of benzene. Number 3, bromine reacts with benzene less readily than with cyclohexene. So cyclohexene isn't the Kekulé structure, instead it's just cyclohexane with 1 double bond. And the reason for benzene reacting less readily than cyclohexene is because of the stability offered by the ring. In Kekulé structure, you would expect it to react with bromine equally as well as in cyclohexene. The double bond is going to react with bromine in exactly the same way because the double bond is localized to this carbon-carbon bond. In the delocalized system, benzene's more stable, so it's less likely to react with the same electrophile. So this also supports the delocalized structure of benzene. So our answers 1, 2, and 3 all support the delocalized model for the structure of benzene. Our answer here is going to be A. In this question, we're told that a solid organic compound can be purified by recrystallization. We're asked which statements about recrystallization is/are true. The organic compound is more soluble in hot solvent. 2. The hot solution is cooled before the purified organic compound is collected. And 3. The melting point of the purified organic compound is lower than the impure compound. So let's start off by thinking about statement 1. The organic compound is more soluble in hot solvent. It's almost universally true for organic compounds or for solid compounds, solid crystal compounds, that solubility increases as the temperature of the solvent increases. Kinetic energy increases, and it becomes more difficult for that crystalline structure to hold its bonding together when the kinetic energy of the solvent molecules is higher. So this is true. Statement 2, the hot solution is cooled before the purified organic compound is collected. So this kind of the idea of recrystallization is that as we increase the temperature, the solubility increases, and the amount of solid that we had originally that was too much to dissolve, it wouldn't dissolve fully in the solvent, will now fully dissolve at a higher temperature, along with any impurities present. The whole point of recrystallization is then to recrystallize, so to cool the solution down and to selectively bring the desired pure compound out of solution as a solid, leaving the impurity still dissolved, and then you can filter off the solid and the solvent which has the impurity dissolved in it. So statement 2 is also true. Statement 3, the melting point of the purified organic compound is lower than the impure compound. And this is definitely not true. The melting point of an impure compound is always lower than the melting point of the pure compound. If we think about a crystal lattice, the presence of impurities is going to interrupt the regularity of that lattice, causing less energy to be required, meaning less energy is required to break that apart. So the melting point of an impure compound is always lower than that of the pure compound. So this is false. So our answer here is going to be 1 and 2, which is B. So our answer is B. In this question, we're asked which of the following could react with the compound below to form a carbon-carbon bond. We've been given this compound and asked if these 3 sets of reagents will have a reaction with it. So the first thing we need to do is think about the functional groups present. First of all, we have a carboxylic acid here. Then we have a carbon-bromine bond. It's a common target for nucleophilic substitution reactions. And finally, we have this phenyl ring. And we'd expect to be looking for electrophilic substitution conditions here. So our first set of conditions is aluminium chloride with chloromethane. And this is going to have a reaction, and it's going to do an electrophilic substitution on the phenyl ring. Our second set of conditions is potassium cyanide in ethanol, and this is going to cause a nucleophilic substitution on our haloalkane bond, our carbon-bromine bond. So this is also going to form a carbon-carbon bond, just like 1. So the electrophilic substitution in 1 adds a CH3 group onto the phenyl ring. It's a carbon-carbon bond. Potassium cyanide here is going to add a nitrile group. It's going to substitute the bromine with a nitrile group. So 1 and 2 so far are both forming carbon-carbon bonds. Number 3, though, we've got methanol and sulfuric acid. These are esterification conditions. So this one isn't going to form a carbon-carbon bond. The hydrogen in the carboxylic acid, well, the OH in the carboxylic acid will be lost, and we'll be left with an ester bond and water. So this doesn't form a carbon-carbon bond. It forms a carbon-oxygen bond. So 1 and 2 are going to form carbon-carbon bonds. That means our answer here is going to be B. This question is about the reactions of organic compounds containing carbon, hydrogen, and oxygen. So that's helpful to begin with. We know that the compounds that we're looking at shouldn't have any other atoms. But we're told that a chemist investigates 2 reactions of alcohol A, shown below. So we've got this alcohol here, and part 1 is asking us, what is the systematic name of alcohol A? So first of all, we already have the compound drawn, so we don't need to draw it for ourselves. But the first thing we should do is to number our chain, find our longest chain. So if we start here, we're going to number 1, 2, 3, 4. So our longest chain is 4 carbons long, which means that this is going to be butan 2-ol. We also have this methyl group here on carbon 3, so the systematic name of this alcohol is going to be 3-methyl butan 2-ol. Part 2 asks us, what is the structural formula of alcohol A? So first of all, we've got these 2 matching methyl groups here. So they're both CH3, and when we have 2 identical groups that are sort of indistinguishable, we put them in brackets and put a number next to them. So 2 of them. Then we have CH, then we have CHOH, and finally CH3. We're told that the chemist heats alcohol A, which I've drawn here, with an acid catalyst to form a mixture containing 2 alkenes. So we know that this is forming an alkene, and the reaction that uses an alcohol as the reagent and produces an alkene as the product is an elimination reaction, where we take the alcohol and one of the neighboring hydrogens, we lose water and gain a double bond. And the trick here is that either of the adjacent hydrogens can be lost to form the double bond. So one double bond is going to form here, and the other double bond is going to form here. So our 2 products, they're both going to have that 4 carbon chain that we started with, and the methyl group, but one is going to have the alkene here, the carbon-carbon double bond there, and one is going to have it here. And neither of them have the alcohol group. In this question, you get 1 mark for each of the structures. We're told here that the chemist heats alcohol A with sodium chloride and sulfuric acid. We need to construct a balanced equation for this reaction, and we need to show structures for the organic compounds in the equation. So we know that we're heating alcohol A with sodium chloride and sulfuric acid. So what is this going to do? Well, our sulfuric acid is going to donate a proton to the alcohol, which will turn it into water, which is then going to leave the molecule with a positive charge, and the chloride anion will replace the alcohol group and we'll be left with a haloalkane. So our products are going to be like this. So in this question, you will get 1 mark for the correct product here, or correct products, and then the second mark will be for making sure that everything's balanced. Is everything balanced? Well, we've got the same number of carbons on both sides here. We've got 1 chlorine on each side. We've got 1 sodium on each side, and we also need our water here. So we'll form both a haloalkane. Since our sulfuric acid donated 1 proton to our alcohol group, it's going to be HSO4 minus, and that's going to form a salt with our remaining sodium, forming sodium hydrogen sulfate. And we're also going to form water from the donation of that proton from the acid to the alcohol group in our alcohol A. Compound B, shown below, is refluxed with excess acidified potassium dichromate 6 to form a single organic product. In this question, we need to complete the equation for this reaction. First things first, we need to think about exactly what acidified potassium dichromate is. And this is a bookwork section of this question, and we need to know that this is an oxidizing agent. It takes things like alcohols and turns them into ketones or aldehydes or carboxylic acids. So we need to look at compound B and figure out what functional groups we have. So we've got 3 alcohols present in this molecule, and I'm just going to circle those. And we need to think about what these are going to be oxidized into. So this OH here, it's bonded to a carbon, which is bonded to just 1 other carbon, making this a primary alcohol. And when we oxidize primary alcohols fully under reflux with excess oxidizing agent, it's going to become a carboxylic acid. Our second alcohol here is bonded to a carbon, which is bonded to 2 carbons, making it a secondary alcohol. And secondary alcohols can only be oxidized as far as ketones. Our third alcohol here is bonded to a carbon, which is bonded to 3 carbons, making it tertiary and meaning that it can't be oxidized by acidified potassium dichromate. However, now that we've thought about the classifications of our alcohols, we can start thinking about drawing our product. So we've still got this 4-carbon chain as our backbone. We've still got this methyl group here on our second carbon. This alcohol was tertiary, so won't be oxidized under these conditions. So this is still present. This carbon here was a secondary alcohol. When this is oxidized, it also abstracts the proton from the carbon, forming a ketone. So we're going to have a carbonyl here. And finally, this carbon is going to be oxidized into, this alcohol is going to be oxidized into a carboxylic acid. So we can add that in here. Now we know that when we do oxidations with acidified potassium dichromate, we form water as a byproduct. So we need to think about how many steps of oxidation we've gone through to balance our oxidizing agent. And we did 2 steps of oxidation with the primary alcohol and 1 step of oxidation with the secondary alcohol. So this is going to be 3 equivalents of acidified potassium dichromate, which has been drawn with this O in square brackets to symbolize an oxidizing agent. And now we've done 2 steps of oxidation from alcohol to carbonyl, which are the ones that produce water. So we need 2 molecules of water, and now this is all balanced. So the 2 marks available here, the first one is for the correct organic product, and the second mark is for the fully balanced equation. The flowchart below shows some reactions of compound C. In the boxes, draw the organic products of these reactions. So first of all, we've got compound C here, which is an alkene with 2 carboxylic acids coming off of the sides, and it's symmetrical as well. So we have 3 sets of conditions. We've got excess methanol and sulfuric acid. We've got steam with phosphoric acid, and we have polymerization. So first of all, we've got these conditions here. We've got the excess methanol and sulfuric acid, and these are esterification conditions. These are hydration conditions here, the steam and phosphoric acid catalyst. Hydration of an alkene is when we turn it into an alcohol. And polymerization is going to be an addition polymerization, where the alkene sort of unfolds, the double bond unfolds and creates a long carbon-carbon backbone. So the organic product from the esterification, we're going to maintain that alkene in the center of our molecule, and we're going to form 2 esters on either side, like so. In compound C, we're going to add steam and phosphoric acid, so we're going to have our carboxylic acids here, and one of these 2 carbons is going to be an alcohol. And finally, with the polymerization, we're going to draw the repeat unit of the addition polymer. Now we need our rounded brackets, N at the bottom, and our trailing bonds going in and out of the brackets on the left and the right.
The general formula for an alpha amino acid is RCHNH2COOH. Part A. The alpha amino acid cysteine, R equals CH2SH, shows optical isomerism. Draw 3D diagrams to show the optical isomers of cysteine. Here we're given the general formula of an alpha amino acid. If we try and draw this as a 3D structure, we would have our central chiral carbon, our R group, a dashed wedge with NH2, and a solid wedge with hydrogen. And then on the same plane as R, we would have our carboxylic acid, or our COOH. But then we need to replace R with the R group that we're given in the question, which is CH2SH, so we can just add this in. And we're asked to show optical isomers, and an optical isomer means that it's got a mirror image. So if we draw the mirror image of this structure, we would again have our central chiral carbon, but our dashed wedge with NH2 and our solid wedge with hydrogen are on the opposite sides, and so is our carboxylic acid group. Our R group remains at the top though, and these are our 2 optical isomers of cysteine. To get the 2 marks for this question, you must have both structures correct. Part B. The alpha amino acid lysine R equals CH2 4 NH2 reacts with an excess of dilute hydrochloric acid to form a salt. Draw the structure of the salt formed in this reaction. So if we draw the 2D arrangement of lysine, we can have our hydrogen, our carboxylic acid group, our amine group or NH2, and then our R group, which is CH2 4 connected to NH2. But we are reacting this with dilute hydrochloric acid. So what happens is we're going to replace the NH2 with NH3+. So this will turn into a 3 and we'll have a positive charge on the nitrogen, and this 2 will turn into a 3 with a positive charge on the nitrogen. But because it's a salt, we also are going to have our chlorines that are paired with these positives, so we'll have Cl- and Cl-. So this is the structure of our salt. If we were reacting with a dilute base instead of a dilute acid, we would change the carboxylic acid group into a carboxylate ion, but because we're reacting with an acid, we're not going to have any effect on our acidic carboxylic acid group. To get the 2 marks for this question, you need to protonate both amines, so turn the NH2s into NH3+, and pair them with your chlorines. Part C. Alpha amino acids can react to form proteins. A short section of a protein chain is shown below. A student hydrolyzes the protein with hot NaOH, aqueous. Draw the structures of the organic products formed from this section of the protein. So what's happening is we're going to break this amide bond when we react with hot base or hot NaOH or sodium hydroxide. And what we produce is our first structure where we keep everything the same except we're adding a hydrogen onto our NH, and then we're going to have a carboxylate ion, so O-, and we need to pair this with an Na+. So that's our first structure. Our second structure is going to be what's left over, so we're going to have a carboxylate ion again, which is paired with a sodium, and then we're going to have the rest of the structure the same until we get to the end where you've got your double bonded oxygen or your carbonyl. Here it's going to turn into a carboxylate again, so you're splitting this bond as well. And finally we need to have our added hydrogen on the NH group. So to get the 3 marks, you get 1 mark for each group that you've hydrolyzed. So that's each O- NH+ that you've written. So in your first product, that's going to be 1 mark, and then in your second product, that's 2 marks. This question is about aromatic compounds. Part A. Phenol undergoes nitration more readily than benzene. Part 1. A student carries out the nitration of phenol with dilute nitric acid to produce 2-nitrophenol and 4-nitrophenol. A small amount of 3-nitrophenol is also produced. The student thought that a carbon-13 NMR spectroscopy could be used to distinguish between these 3 nitrophenols. Explain whether the student is correct. Let's start by identifying the number of carbon peaks in 2 and 3 nitrophenol. So if we start with 2-nitrophenol, we've got 1, 2, 3, 4, 5, 6, because it's an unsymmetrical compound. So it's got 6 carbon peaks. And then looking at 3-nitrophenol, it's also unsymmetrical, so we've got 1, 2, 3, 4, 5, 6 peaks. So it's got 6 carbon-13 NMR peaks. Then we can look at 4-nitrophenol, and this is a symmetrical compound, so we will have fewer peaks because we can draw a line of symmetry down the middle. So we've got 1, 2, 3, 4, because this is also 3 and 2. So it's got 4 carbon-13 NMR peaks, and then we need to link back to the question and say which one is distinguishable. We can identify which one's distinguishable by just writing a little sentence at the end of how many peaks are in which compound. So we can say that 4-nitrophenol is distinguishable and 2,3-nitrophenol is not distinguishable. To get your 3 marks for this question, you get a mark for saying how many carbon-13 NMR peaks are in 2 and 3-nitrophenol, so 6. You get a mark for saying how many carbon-13 NMR peaks are in 4-nitrophenol, so 4. And you get a mark for saying how you can distinguish between them based on this. So that 2 and 3-nitrophenol aren't distinguishable, but 4-nitrophenol is distinguishable. That gets you the 3rd mark. Part 2. Explain why phenol is nitrated more readily than benzene. So, if we decide to talk about how phenol is nitrated more easily than benzene, or more readily, so the first point is that phenol has a lone pair of electrons on the oxygen of the OH in phenol, and this lone pair is partially delocalized into the pi ring system, which is the circle that you draw in your structure. And this means that the electron density is going to increase if you're donating a pair or you're delocalizing a pair of electrons into a ring system. That's going to increase the electron density. And if the electron density is increased, this means that phenol will be more susceptible to electrophilic attack from electrophiles like your nitration of benzene or phenol in the part 1, or in part 2, which we'll come to in a minute, or part B. So to get the 3 marks for this question, there are 3 points that you need to have said. So you get your first mark from saying that phenol has a lone pair of electrons on oxygen, which is partially delocalized into the pi ring system. That's your first mark. Your second mark comes from saying that electron density is going to increase. So that's your second mark. And then your third mark is from saying that phenol is more susceptible to electrophilic attack. Part B. Methylbenzene reacts with sulfur trioxide, SO3, to form D, shown below. The electrophile in this reaction is SO3. Complete the mechanism for the formation of D, show curly arrows and the structure of the intermediate. So our first curly arrow in this mechanism is going to go from our increased electron density, so it's going to be quite negative, to our delta positive sulfur. So negative to positive. And then we're going to kick off this electron group onto our oxygen with the delta negative charge. And then this is going to form the negative that we can see in part D. And we'll have the intermediate with the structure that's going to look like this with our group we want to add. So our sulfur double bonded to an oxygen, double bonded to an oxygen, and singly bonded to an O negative. And we're going to have a hydrogen also attached here because there's hydrogens everywhere along this pi ring system or along the benzene ring. But there's only one because these have alternating double and single bonds. And we're going to have our CH3 group. This is important to keep the same. A lot of marks are lost from not including side chains like CH3 here. And our intermediate is going to have a half ring with a positive charge, which we can donate our hydrogen into. It's important with your half ring that it is in line with your points here and it doesn't go beyond them because then you won't get the marks. And this is everything, because your hydrogen that you're putting back into this ring is going to produce your H plus here. So you can see how you've matched your intermediate to your product. So to get the 3 marks here, you get 1 mark for your curly arrows coming off of methylbenzene. You get 2 marks for having the correct intermediate with the correct arrow from your hydrogen to your positive ring. So that gets you 2 marks. This question is about the hydrolysis of haloalkanes. Part A. The rate of hydrolysis of a haloalkane depends on the halogen present. State and explain how the halogen in the haloalkane affects the rate of hydrolysis. So to get the first mark for this question, we need to explain how, in general, bond strength relates to the rate of hydrolysis. So the first point we're going to make is that the weaker the bond is, this means the faster the rate of hydrolysis, because if it's a weak bond, it's going to require less energy to break, and so the rate of hydrolysis will be faster. And then to get the second mark, you need to compare this to a carbon-halogen bond, like 2 of them, compare them. So, for example, we can have a carbon-fluorine bond, and this is going to be hydrolyzed the slowest out of the halogens, and then you've got carbon-bromine is hydrolyzed slower than carbon-iodine. So this is your second mark. Part B. Chlorocyclohexane is hydrolyzed with aqueous sodium hydroxide. Outline the mechanism for this reaction. Show curly arrows, relevant dipoles, and the products. So in this question, we have a haloalkane reacting with sodium hydroxide. So the type of mechanism we have is called a nucleophilic substitution reaction. So this is one of the mechanisms you just need to know. So we're going to run through the different curly arrows that you need to have, and this is just a set curly arrow thing that you can repeat on every nucleophilic substitution reaction you come across in A-level chemistry. So firstly, on the halogen, so on the chlorine, we're going to have a delta negative, and on the carbon we will have a delta positive. So this is on the carbon halogen bond. And in sodium hydroxide, the nucleophile is our OH minus, which is going to have a lone pair on the oxygen. This lone pair is going to be attracted to the delta positive region, so the delta positive carbon, because negative electrons attracted to the delta positive, and then these electrons are going to kick off the chlorine. So that means our products are going to be a Cl minus, and then instead of having our haloalkane bond, we're going to have an alcohol group. So these are our 2 products that we're going to form in this reaction. So to get the 3 marks for this question, you get a mark for having the correct dipoles, a mark for having the correct curly arrows, and then a mark for having the correct products. Part C. A student hydrolyzes a haloalkane E using the following method. 0.01 moles of a haloalkane E is refluxed with excess NaOH to form a reaction mixture containing an organic product F. The reaction mixture is neutralized with dilute nitric acid. Excess AgNO3 aqueous is added to the reaction mixture. 1.88 grams of a precipitate G forms. Organic product F has a molar mass of 74.0 grams per mole and has a chiral carbon atom. Part 1. Draw a labelled diagram to show how the student would carry out the hydrolysis of haloalkane E. So the labelled diagram that they want is a reflux diagram. So here I've got a round bottom flask connected to a condenser. So this is what you're going to have to draw in this question. And then we need to add some labels. So at the bottom, we have our round bottom flask. This is also called a pear-shaped flask. Either is acceptable in this question. and attached we have a condenser. So we can add these two labels. And with reflux, what you're doing is you're heating. So you're going to heat the round bottom flask. And then you need to describe how the flow of water works in the condenser. So water comes in at the bottom and comes out at the top because you fill it up from the bottom. And then it rises and it comes out at the top, and this keeps a nice flow of cold water coming through the condenser. And this means that your vapours can then get cooled down and then drop back into the round bottom flask. To get the 2 marks for this question, you get a mark for your diagram and then you get a mark for your labels. Part 2. Analyse the information to identify E, F and G. Show your working. Let's start by working out G. So G is formed when you're adding silver nitrate to a reaction mixture and you're forming a precipitate. So this is a test for a halogen, and depending on the different colours of the precipitates, a different halogen will form. So we know that we're going to have silver and a halogen as our precipitate G. So what we can do is we can work out the halogen. So we can use the mass of the precipitate formed and the moles of the haloalkane, because it's going to be the same number of moles in our silver precipitate. So using the equation triangle of mass divided by relative formula mass times moles. So this is going to be 1.88 divided by 0.01. And this gives us 188 grams per mole. So this is the relative formula mass of precipitate G. So to work out what the halogen is, we need to do 188 minus 107.9. This is the relative formula mass of silver. So that gives us 80.1, which means that we've got bromine present because this is the relative formula mass of bromine. So therefore we've got bromine ion with a silver plus ion. So G is equal to AgBr. So in this question we are reacting a haloalkane with NaOH. So this is another nucleophilic substitution reaction. So in a nucleophilic substitution reaction you have a haloalkane and you turn it into an alcohol. So this means that organic product F is going to be an alcohol and it's going to replace the halogen that's in E. So if we work out the molar mass or look at the molar mass of F, this is going to be a 4-carbon backbone. So we're going to have CH3 connected to a carbon, carbon, CH3, we're going to have 2 hydrogens here, and then a hydrogen here with an OH. Because this has the relative formula mass, if we do 12 times 4, so that's the carbons, plus 9, plus 16, plus 1. So the 9 is all the hydrogens, and then the 16 is the oxygen, and then the 1 is the hydrogen in the OH. And this equals 74. So that means this is F. And we can name this as butan-2-ol. So then if we look at E, well, E is when we are replacing the OH with our halogen, and we worked out in the first bit that our halogen is bromine. So E is going to be the same carbon backbone, so 4 carbons, and then we're going to have 2 hydrogens, hydrogen here, and then a bromine for E. For this question, to get your 3 marks, you get a mark for identifying each compound correctly. So a mark for E, a mark for F, and a mark for G. Cinnamaldehyde and methylcinnamaldehyde are naturally occurring organic compounds. Part A. Methylcinnamaldehyde is an E stereoisomer. Explain this statement in terms of the Can-Ingold Prelog CIP rules. So E stereoisomerism is when the highest priority groups are on opposite sides of the carbon-carbon double bond. So looking at methyl cinnamaldehyde, we have the highest priority groups of C6H5 and CHO. And these are on opposite sides of the carbon-carbon double bond. So to get the 2 marks, you get your first mark for naming the highest priority groups as C6H5 and CHO, and your second mark for saying that they're on opposite sides of the double bond.
Part B. A student plans to carry out some chemical tests on both cinnamaldehyde and methyl cinnamaldehyde. Part 1. Suggest a suitable test to confirm that both compounds contain an unsaturated carbon chain. Your answer should include the reagents and observations.
So what this question means is that an unsaturated carbon chain is this double bond here. We're trying to identify that both compounds have a carbon-carbon double bond. So the test for a double bond is you have bromine, so we can say this is Br2 or bromine, and the positive result that if you have a carbon-carbon double bond is it's going to go colourless. So this is what we need to write to get the mark for this question.
Part 2. Describe a chemical test to confirm that both compounds contain an aldehyde functional group. Your answer should include the reagents and observations.
So this question's asking about the aldehyde functional group, which is this CHO in both compounds. So the test for an aldehyde functional group is Tollen's reagent. And if there is an aldehyde present, you're going to produce what's called a silver mirror or a silver precipitate. So this is often one where you get to keep the test tube sometimes because the silver coats the test tube when you test for an aldehyde in the labs. To get the mark for this question, you need to say Tollen's or Tollen's reagent, and it produces a silver mirror.
Part 3. Describe a chemical test to confirm that cinnamaldehyde and methyl cinnamaldehyde contain a carbonyl group. How could the products of this test be used to distinguish between the two compounds? Your answer should not include spectroscopy.
So, first bit of this question is asking us for the chemical test of a carbonyl group. So the chemical test for a carbonyl group is 2,4-DNP, and the positive result is that it's going to produce a orange precipitate. So we can say a PPT, that's a precipitate. So in the next part of this question, we're asked about how we distinguish between the two compounds, and we can't use spectroscopy. So what we can do instead is take what's called a melting point. So there's melting point tests you can do, and then you can compare this to a known value in order to distinguish between the two compounds. So, and compare to a known value. So this is a great alternative to spectroscopy, and it's really quick because the machine will heat up quite rapidly to the temperature you set it to, and then you can slowly increase it from then on, and you can very accurately determine the melting point of your crystals. And this is something you can do instead of spectroscopy. So to get the 3 marks for this question, you get 1 mark for the chemical test for a carbonyl group, and then you get 1 mark for saying take a melting point, and 1 mark for saying compare to known values.
Part C. The flowchart below shows some reactions starting with cinnamaldehyde. Draw the structures of the missing organic compounds in the boxes and add the missing reagents on the dotted line.
So the secret to answering these questions well is that you know your reaction map. So this can be found on the exam board's website, and you can print it off and just draw it out lots of times so that you really get it in your head. So if we start with the product in the top right, we've got excess hydrogen and a nickel catalyst. So what this is going to do is it's going to reduce the carbon-carbon double bond, and it's going to reduce the nitrile group here, and it's going to form an amine. So if we draw out our new product, we're still going to have this phenyl group. we're going to have the single bond, and then we're going to have CH2NH2 and our OH group. So it's the same except these two groups have been reduced. Okay, so moving on to the bottom right product. So we have this H+, this acid, and this is going to react with our nitrile. And everything else is going to remain the same. So we're going to have our phenyl group here. We're going to have the carbon-carbon double bond. And then we're going to have a carboxylic acid instead of this nitrile. And then everything else is the same. So this is your product in the bottom right. Now let's look at our last product we have to draw. So NaBH4, this is a reducing agent, and it's going to reduce our aldehyde functional group. So everything's going to stay the same except our aldehyde is going to turn into an alcohol. So here, keeping it all the same except we have an OH. And then finally, thinking about the reagents to turn succinimide into this other product, well, we need to react it with NaCN and H+. So this is going to convert your aldehyde into your hydroxynitrile, which is the product on the right. To get the 5 marks for this question, you get a mark for the bottom left product being correct, a mark for the bottom right product being correct, a mark for the correct reagents, and then 2 marks for the top right product being correct. Part D. Methyl cinnamaldehyde reacts with iodine monochloride, ICl, by electrophilic addition. The reaction produces a mixture containing 2 different organic products. The electronegativity values of chlorine and iodine are given in the table below. Outline the mechanism using the curly arrow model for the formation of one of the organic products and explain which of the 2 possible organic products is more likely to be formed. In your mechanism, you can show the phenyl group as C6H5. So in this question, we're told we're doing an electrophilic addition mechanism, and we're reacting with ICl. So in electrophilic addition, you have your carbon-carbon double bond, and then you're going to add some substituents onto this. Commonly, you do this with HBr or just bromine, but here we've got ICl. So if we redraw the methyl cinnamaldehyde and use the phenyl group as C6H5, so redrawing this, we have our carbon-carbon double bond, we have our aldehyde group, our methyl group, a hydrogen, and then we have our phenyl group of C6H5. Important that we have the carbon bonding to the carbon. So then we have ICl, and using the Pauling electronegativity value, we know that chlorine is more electronegative. So it's going to have a negative dipole, and iodine is going to have a positive dipole. And then it's just the same as any other electrophilic addition. So we have our double bond being attracted to the delta positive, and then an arrow kicking off our chlorine, and this is going to produce our carbon-carbon single bond with our aldehyde functional group, our CH3 group or methyl group, our hydrogen, our phenyl, so everything being the same except we're adding this iodine here, and we're going to have a positive charge on this other carbon, and we're going to have Cl- left over, which is going to be attracted to this positive charge, and we'll produce our product carbon, carbon, CHO, so our aldehyde, our methyl group, our chlorine, hydrogen, iodine, and then our phenyl group to finish. So this is our major product. So the question does say that we only need to show the formation of one organic product. So this is the major, and then if you had the iodine go on to the other carbon, you would produce the minor product. So this would be CCCHO, CH3, I, Cl, H, C6H5. And this is because you've produced a secondary carbocation intermediate rather than the tertiary carbocation intermediate that you have in the mechanism which we've drawn here. So this is our minor product. Either mechanism will get you the marks for this question. So it doesn't matter if you do minor or major, as long as the mechanism is correct. So here I've just written a little explanation, most stable carbocation intermediate. So that's what I said about having the tertiary carbocation intermediate in this mechanism that we've drawn. So to get the 6 marks for this question, it's a level response question, so there aren't set marking points, but you need to have an outline of the mechanism for the formation of either product, which is mostly correct, and the major and minor products are identified with a correct explanation for which product is the most or least likely to be formed. So here we've said why it's the most likely to be formed, because it's the most stable carbocation intermediate. This question is about aromatic carboxylic acids and their derivatives. Part A. The flowchart below shows some reactions of compound H. In the boxes, draw the organic products of these reactions. So let's start with the top left product. So we're reacting with a carbonate, and carbonates react with acid. So we look at the acid group of compound H, which is our carboxylic acid. And what a carbonate does is it turns the carboxylic acid into a salt. So we're going to have a carbon, a double bond oxygen, an O negative, and Na plus. The Na plus coming from our sodium carbonate reagent. And then we have our OH remaining the same. So this is our top left product. So then if we look at NaOH, which is our top right product, this is going to react with the OH group and the carboxylic acid group. So if we circle these on compound H, here we have our carboxylic acid and our OH group. So what's going to happen is similar to the top left, where we have our carboxylic acid turning into our O minus Na plus, so our salt. And then the same thing's going to happen to the oxygen. We're going to have an O minus and an Na plus. And we keep our ring the same. So then finally, our bottom product, we're reacting with bromine, and this is going to be what's called an electrophilic substitution on the benzene ring. So what's going to happen is it's going to substitute next to the OH. So we're going to have our ring the same, our carboxylic acid group the same, our OH group the same, and then next door to it we're going to have a bromine that's substituted onto the ring. To get the 3 marks for this question, you get a mark for each correct product. Part B. Compound H is used in the synthesis of polymer I, as shown in the flowchart below. Complete the flowchart by drawing the structure of the acyl chloride and 2 repeat units of the polymer I, and stating the formula of the reagents required for this first stage on the dotted line. Let's start by drawing our acyl chloride. So an acyl chloride is a carbonyl group, so we're going to have our C double bond O, but instead of the OH in the carboxylic acid, we have a chlorine. But the rest of the compound stays the same. The reagents for turning a carboxylic acid into an acyl chloride are SOCl2. So it's just one reagent here. And now we're asked to draw 2 repeat units of polymer I. So polymer I is when you're having the acyl chlorides reacting together. So this is a similar process to when you have a carboxylic acid and an alcohol, where you produce a polyester and water. But instead of producing the water, we're going to produce hydrochloric acid, because we're going to have our hydrogen and our chlorine rather than having our hydrogen and our OH. So the ester is the same, it's just the byproduct that's different. So we're going to have our 2 repeat units, so our rings connected to our ester functional group, and then another ring, and just to show that it's an ester, we're going to have a C double bond O, then a dotted line, and an oxygen with a dotted line. And then make sure we show that they're rings by drawing the circles. In this question, you get a mark for the correct reagent, a mark for the correct acyl chloride group drawn. You get a mark for having an ester link in your polymer, and then you get a mark for having the rest of the structure correct. Part C. A cosmetic product containing 4 esters J, K, L, and M is analysed by gas chromatography and mass spectrometry. The results are shown below. The number of peaks are the relative molar proportions of the compounds in the mixture. Part 1. The concentration of ester K in the cosmetic product is 9.13 times 10 to the negative 2 grams per decimeter cubed. Using the results, calculate the concentration in moles per decimeter cubed of ester M in the cosmetic product. Give your answer to 2 significant figures. So the first key bit of information in this question is that we're given the concentration of ester K, which is 9.13 times 10 to the negative 2 grams per decimeter cubed. So if we use the MZ of K, we can work out the concentration in moles per decimeter cubed, because that's what we want our final answer in. But we do want it of M and not K, so this is just something to be wary of in the later bit of the question. So if we divide 9.13 times 10 to the negative 2 by 166, we get 5.5 times 10 to the negative 4 moles per decimeter cubed. And this is because if we have grams per decimeter cubed divided by grams per mole, because this is what MZ is measured in, we cancel out our grams and we end up getting moles per decimeter cubed. So here we've got the concentration of K, and we eventually want the concentration of M. So if we look at the areas, we've got M is 5.9 and then K is 4.3. So what we can do is we can take 5.5 times 10 to the negative 4 and multiply this by the proportion. So we can do 5.9 divided by 4.3, and that equals 7.5 times 10 to the negative 4 moles per decimeter cubed. And we want our answer to 2 significant figures, which it is at the moment, so that's great. So we can put 7.5 times 10 to the negative 4 as our final answer. In this question, you get a mark for the concentration of K, so 5.5 times 10 to the negative 4, and a mark for the concentration of M, so 7.5 times 10 to the negative 4. Part 2. A general structure for esters J, L, and M is shown below, where R is an alkyl group. Use the mass spectrometry results to deduce possible structures for esters J, L, and M. So here I've just drawn the general structures, but leaving out the R groups. We're told in the question that the R group is an alkyl group, so it's made up of carbon and hydrogen. So we can start by working out the relative formula mass, or the MZ, of the general structure. So that's going to be 1 for our hydrogen, plus 16, so that's our OH, plus our ring of 6 carbons, so that's 12 times 6, plus 4 hydrogens, plus a carbon, and then plus 2 oxygens. And that equals 137. So if we look at the MZ values for J, L, and M, so we have J, L, and M, we can work out the relative formula mass of our R groups. So that's going to be minus 137, that equals 15. Then minus 137, minus 137, we have 43. So using this information, we can work out what our R groups are. The first one we can start with is J, so 15, that's going to be CH3, because carbon has a relative formula mass of 12, 12 plus 3 is 15. So L and M are going to have the same R group value in terms of their relative formula mass. So you can put them either way round because there's no way of knowing which one's which based on the information that we're given. So if we work out how many carbons are present, we do 43 divided by 12, and that equals about 3.6. And you can't have 0.6 of a carbon, so we're going to have 3 carbons. So we do 12 times 3, and this equals 36. So we need to do 43 minus 36, and that equals 7. So we're going to have 7 hydrogens present. So we can have just a long group chain, so we can have CH2, CH2, CH3. This is going to give us 7 hydrogens and 3 carbons, so it equals 43. Or we can have CH and then CH3 brackets 2. This also gives us 7 hydrogens and 3 carbons. To get the 3 marks for this question, you get a mark for each correct structure for the esters. You can have L and M the other way round though. The relative molecular masses and boiling points of some fuels are shown in Table 22.1. Part A. Write an equation for the incomplete combustion of heptane. The general structure of an alkane is CnH2n plus 2. Heptane has 7 carbons, so has the structure of C7H16, because then that's following the general formula. Combustion means a reaction with oxygen, and it's incomplete combustion, which means that we produce carbon monoxide and not carbon dioxide. Carbon dioxide is complete combustion. But we also produce water. So now we need to balance the equation. We need 7 carbon monoxides because we have 7 carbons. And then we need 8 waters because we've got 16 hydrogens. And then balancing the oxygens, we need 7.5. To get the mark for this question, you must have the full equation correct for the incomplete combustion of heptane. Part B. Explain the difference in boiling points of the fuels in Table 22.1. If we start by comparing heptane and hexane, heptane is a longer carbon chain than hexane, so it has more points of contact. So this is going to be our first bullet point and our first marking point for this question. So then our second bullet point or marking point is that because heptane is a longer carbon chain, that means it's got stronger induced dipole-dipole interactions because of its more points of contact. So that's our second marking point. And then our third marking point is that pentan-1-ol can form hydrogen bonds which are stronger than induced dipole-dipole interactions, because the more energy is required to break hydrogen bonds over induced dipole-dipole interactions. So to get the 4 marks for this question, there are 4 bullet points that I'm writing here, and each of these bullet points is a marking point for this question. And as you can see, the bullet points correspond with the boiling points because more energy is required to break hydrogen bonds, which is why pentan-1-ol has the highest boiling point, and that heptane has stronger induced dipole-dipole interactions, which is why it's got a stronger boiling point or a higher boiling point than hexane. So it follows the trend that we're shown in Table 22.1, and therefore we're making sure that we're answering the question correctly and to our fullest potential. Fuel additives are often used to improve the combustion of a fuel. Part 1. Compound N is a fuel additive containing carbon, hydrogen and oxygen only. Complete combustion of 1.71 grams of compound N produces 2.97 grams of CO2 and 1.62 grams of H2O.
The relative molecular mass of compound N is 76.0. Calculate the molecular formula of N and suggest a possible structure for the compound. The first thing we're going to do in this question is work out the moles of carbon dioxide and water using the equation triangle of mass divided by relative formula mass times moles. So if we start with carbon dioxide, we're given its mass of 2.97 grams, so 2.97 divided by 12 plus 16 times 2, so that's the relative formula mass of carbon dioxide, gives us 0.0675 moles. Then doing water, so we've given its mass of 1.62 grams, so it's going to be 1.62 divided by 1 plus 1 plus 16, which is the relative formula mass of water, and that gives us 0.0900 moles. Then we need to work out the ratio of carbon to hydrogen. So carbon dioxide to water is 3:4, but there are 2 hydrogens in water, so that means the actual ratio of carbon to hydrogen is 3:8. So then we can work out the molecular formula will be C3H8, and then we need to work out how many oxygens there are, so we can use the relative molecular mass of 76 to work this out. So that would be 76 minus 12 times 3 plus 8, which equals 32. And then we need to divide by 16 because that's the formula mass of oxygen. So that's going to be 32 divided by 16, which equals 2. So we have 2 oxygens. So now we need to suggest a possible structure. So we could have 2 alcohol groups, which could be at the end of our carbon backbone chain, and then we fill the rest with hydrogens. Alternatively, you could have the oxygens in between the chain, so you could have carbon, oxygen, carbon, oxygen, carbon, and then your hydrogens, just so long as you make sure that the molecular formula of C3H8O2 is shown in all your structures that you present, but you only need one possible structure. But either are fine. You could also have the alcohol groups in different locations along the carbon backbone chain, as long as you have the correct molecular formula shown in your structure. To get the 5 marks for this question, you get a mark for working out the moles of carbon dioxide, a mark for working out the moles of water, a mark for working out the ratio of carbon to hydrogen, not a mark for working out the ratio of carbon dioxide to water. You get a mark for working out the molecular formula of N, and a mark for a correct possible structure of N. Part 2. Sulcitol has been investigated as a potential fuel additive. Sulcitol is synthesized from propane 1,2,3 triol and a carbonyl compound. Construct a balanced equation for this synthesis. Show structures for the organic compounds in your equation. So let's start by drawing propane 1,2,3 triol as our first reactant. So we have our carbon backbone and our 3 alcohol groups at carbons 1, 2 and 3. Then we have a carbonyl compound that we're reacting. So the carbonyl compound that we're using in this question is going to be a ketone, and it's going to be propanone. And then we're going to form our sulcitol, so we can draw this out again, just copying what's given in the question. And this is what's called a condensation reaction, so we also produce water as a byproduct for this reaction. To get the 2 marks for this question, you get a mark for identifying that the carbonyl compound is propanone, and then you get a mark for the rest of the equation being correct. Part D. A scientist is researching compounds that might be suitable as fuel additives. One of the compounds gives the analytical results below. Elemental analysis by mass: carbon 54.54%, hydrogen 9.10%, oxygen 36.36%. The mass spectrum has a molecular ion peak at MZ 132.0. The proton NMR spectrum in D2O, where the numbers by the peaks are the relative peak areas. When the spectrum is run without D2O, there are two additional peaks with the same relative peak areas at 11.0 ppm and 3.6 ppm. Use the information provided to suggest a structure for the compound and show all your reasoning. So our first step is going to be to work out the molecular formula, and we do this by working out the empirical formula and then using the mass spectrum data. So working out the empirical formula, we need the elemental analysis by mass. So what we do is we take each percentage, so 54.54, 9.10 and 36.36, and then we divide by the relative atomic masses of carbon, hydrogen and oxygen. So for carbon that's 12, for hydrogen that's 1, and for oxygen that's 16. So for carbon that equals 4.545, for hydrogen that equals 9.10, and for oxygen that equals 2.273. Then we divide by the smallest, which is 2.273, and we do this for each of the values we've calculated. And then we get a ratio of 2 to 4 to 1. So that means we've got 2 carbons to our 4 hydrogens and our 1 oxygen. And this is the empirical formula. Working out the molecular formula, we need the mass spectrum data. So this has a relative formula mass of 12 times 2 plus 4 plus 16, which equals 44. And we've got a molecular ion peak of 132. So we do 132 minus 44, or divided by 44, sorry, and that equals 3. So our molecular formula is going to be our empirical formula times by 3. So that's C6H12O3 is our molecular formula for our compound. So if we look at this hydrogen environment 1, so that's got a chemical shift of 4.0 ppm and a splitting pattern of a quartet. So this could be CH3CHO as an environment that it's connected to, and the hydrogen that would produce this would be this hydrogen here because it's got a 1 next to it, which means that there's 1 hydrogen in this environment. So looking at number 6, so this has a chemical shift value of 1.3 ppm, and it's got a singlet splitting pattern with 6 hydrogens in this environment. So this could be CH3 brackets 2 connected to a carbon, and the hydrogens that would give this peak are these ones here, the hydrogens attached to this carbon with 3 of them around it. So now moving on to 3, so this has a chemical shift value of 1.2 ppm, and it's got a doublet splitting pattern with 3 hydrogens in its environment. So it could be CH3CH, where the hydrogen responsible for this would be these hydrogens here. Again, the hydrogens attached to this carbon where there's 3 of them. The way that you can identify the splitting patterns is you look at how many hydrogens are next to your hydrogen. So for the first environment, you've got 3 next to it. So you're going to have 4 lines because it's how many is next to it plus 1. So your singlet, you've got none next to it. So you're going to add 1, which means you've got 1 line. And then in your doublet, well, you've got 1 hydrogen next to your environment. So you add 1 to 1, so that means 2. So you've got 2 lines, which is a doublet. Now looking at our D2O peaks, we have one with a chemical shift value of 11.0 ppm and one with a chemical shift value of 3.6 ppm. So we can use our data books for these. We know that D2O is going to remove any oxygen-hydrogen peaks. So we look for ones with an OH in their group. So the chemical shift value at 11 ppm, that's a carboxylic acid, or COOH. So the hydrogen in question is this one on the end. And then at 3.6 ppm, this is an OH peak. So the hydrogen that is removed is this hydrogen here. And now we can suggest a structure for this compound. So we need to make sure that we've got the molecular formula correct and we're meeting all of these hydrogen environments. But we can label them after we've suggested a structure just to double check that we've got everything correct. So if we have CH3 connected to a 3-carbon backbone with a carboxylic acid on the end, and we have our alcohol groups. So already we've met the D2O peaks. And then we have CH3, CH3, and a hydrogen to make sure our molecular formula is correct. So now we can look at the hydrogen peaks and we can label them. So starting with our D2O peaks, we have our 11.0 ppm hydrogen here in our carboxylic acid, and we have the 3.6 ppm hydrogen in this OH group. So then looking at the first hydrogen environment, we have this quartet. So this quartet is going to be this hydrogen here, a 4.0 ppm, because it's connected to our CH3, so we're going to have a 4 hydrogen splitting pattern. So now looking at number 6, so this number 6 is going to be a singlet, and it's going to be these hydrogens here, so 1.3 ppm and 1.3 ppm, because that has 6 hydrogens, because we've got 3 and 3, so 6, and the carbon it's connected to doesn't have any hydrogens attached to it, so it will have a singlet splitting pattern. And finally, our doublet, that's going to be this one on the end with our 1.2 ppm, because it's connected to a carbon with 1 hydrogen, so it's going to have a doublet splitting pattern. So we've checked that all of the data we've been given matches the structure that we've suggested, because the molecular formula is correct. We've got 6 carbons, we've got 12 hydrogens, and we've got 3 oxygens, so that's correct. And we've double checked that all of our hydrogen environments match the hydrogen NMR that we've been given in D2O and the 2 additional peaks without D2O. So this is a level response question, which means that there aren't set marking criteria. Instead, to get the 6 marks for this question, the suggested structure shown must have a C6H12O3 molecular formula that's consistent with the splitting pattern and chemical shifts in the NMR spectrum. And you must have comprehensive reasoning with most of the data analysed. So in this answer here, we've analysed all the data and we've shown that we've confirmed that the NMR spectrum peaks match our suggested structure. So this would get 6 marks.